Okay, so the last part of section 9 is something called infinite limits. Okay. And basically, the gist of what we're going to do is more practice with estimates. Okay, so we're going to do just like epsilon n arguments, but the version that involves infinity. So there is one kind of divergence that people single out. Okay, so and it's what we call convergence to infinity. Okay, so definition: if you have a sequence S of n, a sequence, and so what we're talking about is some sequence that goes off, that goes off to infinity. Okay. So normally we call that, up until now we've called that just one kind of, we would say that the sequence diverges. Okay, but from here on in we're going to call this the sequence converges to infinity. Okay, or you could say diverges to infinity. Okay. So we want to describe this mathematically rather than just say it gets bigger and bigger. If you have some sequence that has the following property, then we say that it converges to infinity. So if given any number, and usually we assume that that number is positive. If given any positive number, there exists an n such that being past that n ensures that your sequence exceeds the number, then we say that the limit of S of n is infinity. Sn goes to infinity. And that Sn goes to infinity. Yeah?
I'm a little confused because what if your limit is 2 and you let m be 1? Then when any m?
If given any m, so if I give you an m, so if given any m, there's an n that satisfies it. So we're not playing in this case, previously we played the epsilon n game. Now we're going to say that your limit is infinity if you can play the mn game. Okay, so like no matter what m you're given, there's a time past which you exceed it, right? So if I say I want everybody to be bigger than 1,000, there's a time past which it happens. I want everybody to be bigger than 1 billion, there's a time past which it happens, right? So you can't just say you can't just play the mn game for one m. You have to be able to play it for any, right? If no matter what m you're given, you can defeat it. Okay, there's a time past which you always exceed that m. Okay, so right, so I don't know if we need to do a simple example, but if we wanted to do a simple example, we'd say the limit of n is infinity as n goes to infinity. Right. So, right, you need to show that given any m, there exists an n past which n exceeds m. Right. It's need an n such that if n exceeds n, then n exceeds m. Right. Well, what are you going to take as your n? M. Right. The end. Right. So take n to be m itself. Certainly if m exceeds n, which is m, then n is bigger than m. Okay. So yeah, so the limit is infinity here. more interesting is to do some require some sort of intermediate bound. So here's one that we could do this way. The limit of n squared plus 1 over n as n goes to infinity is infinity. Okay, so as usual, we're going to do some scratch work, right? We want n such that n exceeds n ensures that n plus 1 over n is bigger than m. Okay. Now, what we're going to do is we're going to use an intermediate bound. We'll find something that's smaller than this, but easier to deal with. Okay, and that thing will be just n squared over n. The n squared over n is certainly smaller than n squared plus 1 over n, right? This thing is of course 1 over n. 1 over n.
You mean n?
I'm sorry, is n. Is n. Right. So you see that if we take so as long as n exceeds m, we're good. Right, so we can take as our n, we just use m. Okay, so it's pretty similar to what we did before, but this time we're gonna get intermediate lower bounds rather than some intermediate upper bound. Right, previously we had something like this, s of n minus l, and then we tried to find something larger than it, and we said, well, if that thing is smaller than epsilon, then we're okay, right? And we try to choose something that we can relate back to the distance between the size of n, basically. Okay. Now we need to do sort of the opposite. We need to find something smaller. Right. Okay, so that's our scratch work, right? And then you, as usual, you write it up. You'd say, okay, proof given m, let n just be equal to m. Right. Then, if n exceeds n, which is m, we see that n squared plus 1 over n is bigger than n squared over n, which equals n, which exceeds m. Right? So, right, n squared plus 1 over n exceeds m. Whatever for these terms.
Thank you.
Right. So we've successfully played the m game. Okay. Any questions? Any questions? Okay. Let me do a couple more examples. They're sort of along the same lines of what you've seen before, so here's one. The limit of n squared plus 1 over n plus 2 is infinity. As n goes to infinity. Okay, so, again, we want an n such that if you're bigger than n, then this thing is bigger than m. Okay, and right? We could play the same trick and just get rid of that 1 up there, but then, it's still not that clean. So what we'll throw in an additional trick to make it cleaner. And we'll say, well, look, observe that n plus 2 is bigger than 2n. I'm sorry, is smaller than 2n. Smaller than 2n, as long as n is bigger than 2. Right? You see what I'm going to do? I want to replace this thing with an n, right? I'd like to get rid of this 2. Right? I'd like to replace this with an n, but you see if I divide by something smaller, it's going to get bigger. Right? So I want to divide by something bigger. I want to divide by a multiple of n rather than get rid of this 2. I'm going to change this thing to 2n. Okay, right? So I take this thing, and I say, okay, well then, if that, so for n bigger than 2, I have that this thing is bigger than n plus 1 over 2n. Right? Now I've got the n that I hoped for. Right? And I see that this is, of course, bigger than n squared over 2n. That's to say, n over 2.
And from n over 2.
Then, right, I want, so from here, I want this thing to be bigger than m, right? But that's easy, right? As long as, that's the same as saying that n should be bigger than 2m. So you're sort of hoping to get an n, right? You're hoping to get something that looks like n over here, because then you can say, well, then if n is bigger than m, then I'm okay.
And even though it's a fraction, we could just, like the way you would do it is you'd say, for n greater than capital N, where n equals 2n, right?
Yeah. Yeah. Okay. So we need two things to happen, right? We need n to be bigger than 2m, but we also need n to be bigger than 2. So what we'll do is, when we write the proof itself, we'll say, given m, let let capital N be the max of 2 and 2m. Then, if n is bigger than that, then we know that n is bigger than 2 and n is bigger than 2m. Right? If n is bigger than n, we see that n squared plus 1 over n plus 2 exceeds n squared plus 1 over 2n. By star, okay, which exceeds n squared over 2n, which equals n over 2, which is bigger than m by dagger.
So it's like the n equals max, is that just a bound?
That is the n that we're looking for, right? We choose n to be the larger of 2 and 2m. Right, you see that we needed in order to make this thing, right, we come back to here, we look at this thing. in order to make this thing bigger than m, right? In order to make this thing bigger than m, right? This is our goal, right? To make this thing bigger than m. Somebody gives us a bar. We want to make this thing over the bar always, right? In order to make this thing bigger than m, we need if we can get this thing bigger than m, that's good, right? So what we need is that little n has to be bigger than 2m, right? But we also, along the way, used this fact. And that fact relied on n being larger than 2. Okay, so we need to ensure two things, right? That little n be bigger than 2, and little n be bigger than 2m. And this is how we do it. We say let n be the larger of 2 and 2m, right? Then that'll do it for us. Okay. Any questions? Okay. Sorry. I left out. Suddenly spasmed. I kind of pushed myself yesterday. I do this peculiar, like, Chinese martial arts practice where you stand still for an hour, but you have to hold yourself in a certain posture. So you imagine that you're holding a ball, like you go like this for an hour or something like that. Right. Or the worst one. The one that I'm actually working on now is you actually go like this. This is actually, so you keep your shoulders up, let your arms relax, like this. And you're actually supposed to be standing on a ledge so that the backs of your feet are off the ground. And you just stay like that for an hour.
What do you do during the hour?
Oh, you try to relax, actually.
Oh, so you're not like watching TV or?
No. No, it's like a mind-body connection thing. So you're like trying to establish this really interesting control between your body and your mind.
Wow. It's tiring.
Yeah, but it's really fascinating. It's really fascinating. I wouldn't do it if it weren't really interesting.
Well, when do you teach this class?
This semester, Tuesdays and Thursdays, from 4:10 to 5:15.
Wait, this is a class?
Yeah, I teach it as a class. It's called
wow.
standing practice. Yeah, I've been into martial arts since I was a kid. That is, since my parents allowed me to do it. Because they were worried that I would kill somebody. They didn't allow me to start until I was 14.
Do you have a lot of other moves?
No, I don't. And further, I injured my back 3 years ago, so I basically can't do anything. But I can stand still.
Are you offer that course next semester?
I am, but actually I'm going to I should erase this from the video. So I'm actually going to offer 2 courses. So I do, my main martial art is Aikido. And that's something I've done for 30 years, except the last year I've sat out because I'm trying to heal my back, or trying to rehabilitate my back. And then the second thing that I'm really interested in now is this mind-body thing that, because you're doing the standing, and it's just so fascinating to feel your bodily sensations and your pulse and your it's the human body. I mean, we don't really pay attention to it. We ignore it all the time. We filter it out. But if you actually pay attention to what's going on, it's just crazy. Energy surge. All this stuff is going on, and we just ignore it. It's really fascinating.
How do you evaluate one in a course kind of setting?
If they can go through it.
If they just stand for an hour.
If they stay, I mean, yeah. So I can't judge their mental state. That's the thing, right? But if the person comes 2 hours a week and does this for the whole term, standing in silence, they pass. Right? I mean, most people can't do that. Yeah, most people, will drop out. Whoever lasts to the end passes, basically. Yeah.
How do you feel different after an hour of doing this?
Do you guys want to hear about this? I mean, it's sort of this is not really relevant, but okay. So the first thing that people do is just stand, and there's no physical, there's nothing like, there's no difficulty to it. You just stand and you empty your mind, and you breathe naturally, and you try and release tension as much as possible. And then you think about two things. One is you imagine that you tell your body sit down, but you don't sit down. You also tell your body, suspend yourself from the top. So, like, imagine that there's a line suspending you from the top of your head. Okay. And you just do that. Okay. And you pay attention to your body. Now, the interesting thing is that, of course, we regularly ignore our body, right? But so paying attention to your body just becomes really interesting. And what they said to me at the beginning was that we're not going to tell you what's going to happen, what you're going to feel, because we don't want to prejudice what you're going to experience. And so I sort of feel like I don't want to say too much about what you would experience. But so what happened to me is that, like, after 1 week, I said, well, I have this sensation and this sensation, this sensation. And I said, okay, what's going to happen next is this. And then, like, soon after that, kablam, this something happened, right? And I was like, oh wow, these guys know what they're talking about. And then, so, like, it's really interesting. And then from there, from this sort of initial increased body awareness bit, and increased awareness of how your mental intent affects your body, then you move on to sort of more strenuous things. So, and then later on you start fighting people. Yeah, much later. I've been doing the standing for 2.5 years now. I'm still nowhere near, like, actually hitting somebody. Yeah, like, I was doing Tai Chi for a long time, and they said, don't do any more Tai Chi. Don't do that. Just do the standing. Don't do anything. Just do the standing. Yeah, and it's been really interesting. Okay, back to it. So next semester I'm going to try to do the Aikido again, but just 1 day a week, and I'll do the standing also 1 day a week. So if you're interested, I will be doing the standing practice next semester. Okay, so here is something. So if r is bigger than 1, then the limit of r to the n is infinity, as n goes to infinity. Okay, and so I want you to think about this, see if you can get anywhere with it. I said X, meaning exercise. So here's a hint. Use the binomial theorem. Okay, so see if you can take a few minutes and see if you can think about how the binomial theorem might be used to show that this goes to infinity. Along the lines of how we used the binomial theorem in the last class. Yeah, just for your amusement, over the summer I was in China, and I went to the place where they actually practice, like, standing practice very seriously. I just went for one 24-hour period, but in that 24-hour period, I did like 8 or 9 hours of standing.
Do they have, like, really intricate positions? Or do they really advanced?
They're like stances that are more related to fighting, and then they have like a whole series of exercises, and then a whole series of like two-person exercises, and then like things that get closer to fighting, and then actual fighting.
What's the longest period you stood?
3 hours, 2.5 hours, something like that. Yeah.
Is it possible to do induction with limits? Or does that not make sense?
What would you induct on? What would be your index?
Probably n, but that's what I'm thinking. It doesn't make sense because n is going to infinity.
Yeah, no.
This is only talking about what happens when I do this, not it.
Yeah. I mean, you could induct on the. Let me think. Maybe you could induct on the m. Right? You would say, let m equal 1. Then I know that the limit is bigger than 1 because my r is bigger than 1 to start off with. So the base case is proven. Now assume that for an arbitrary m, that you know that there's some time past which you exceed it, right? Could that give you, can you use that fact to show that there must be a time for m plus 1? Like maybe that would be the way to use induction. Does anybody have an idea? Anybody have some idea? If you don't, I think this is a pretty cool problem, so I'm going to just put in the homework, I think. Yeah, Mitchell, you have something?
Would you start by saying R is equal to 1 plus B,
Yeah.
where B is
That'd be
larger
great.
than 0?
That'd be great. Okay, so I'll let you, Mitchell has given you another go ahead. And yeah, we'll put it in the homework. That's a cool problem. At least you're here.
Yeah, so you say R is equal to 1 plus B, but B larger than 0.
At least you're here. That's a very positive way of looking at it. It's true. At least you're here. Okay.
Questions I'm standing up to take these off.
Okay, so there are a couple more results in this section. First, so theorems for limits and infinity. Okay, the first one is about the limits and arithmetic, right? So, so what kind of limits and arithmetic theorem do we have? We have something like this. So if you have a sequence that converges to infinity, and you have another sequence that is bounded below by, bounded below by some constant, then one a sub n plus b sub n also converges to infinity. In my notes it says diverges to infinity, but anyway. A sub n, b sub n converges to, also the product converges to infinity, provided that k is bigger than 0. And the third one is sort of obvious, that C a sub n converges to positive infinity if C is bigger than 0, and to negative infinity if C is less than 0. Okay, so let's think about, we're only going to prove the first one. Let's think about why that makes sense, right? Why does that make sense? Why does number 1 make sense? Right, you have two sequences, one of which goes off to infinity, and you have another that's bounded below by some k. Right? So this other guy doesn't necessarily converge, but it's bounded below. Okay, and what we're saying is that the sum is going to go to infinity, right? So what does that mean? For the sum to go to infinity means that given any height, there's a time past which you exceed that height. Okay, so we know that given any height, there's a time past which the a sub n's will exceed that height, right? So what about a sub n plus b sub n, right? Well, this makes sense, right? It seems clear, right? Because the b sub n's are all bigger than k, so at the worst, you know, this would drop down. The a sub n's would drop down by k, right? So to ensure that everybody's bigger than m, to ensure that the sums are bigger than m, just find the place where the original guy is bigger than m plus k, right? Plus the absolute value of k, excuse me, right? So, okay, so, what's that? M minus k. Yeah, m minus k. Okay, so that's the idea, and let's give the proof, right? So we know that given any m, there exists an n such that if n exceeds n, then we have a sub n exceeds n. Okay. So, in particular, so given some m, choose n such that n exceeding n ensures that a sub n is bigger than m minus k. But then a sub n plus b sub n is bigger than n minus k plus k, which is m.
Professor?
Yeah.
I thought it's really important, but is it a sub n plus b sub n is greater than or greater than and equal to? Because if we're setting the bound at k, could it, if it's bounded by k, does that mean like approaches only, or could it also equal k?
Yeah, it could be either one, actually. I mean, when people say bounded below, I mean, you're right. It could either be, we could either mean this, or we could either mean this. So it could be either one. But even if it's this one, we're still okay, because a n being strictly bigger than this, and this guy being greater than equal to the other, both of that together would ensure that this happens. So it doesn't matter. It doesn't matter in two senses. Right? First off, we could just say we mean this, but even if we don't do that, it's still right. Okay. So right. So that's it. Right. Okay. Let me just put up one last. So I'm not going to prove the rest. You can read it or do it as an exercise. The last thing in this section is the following result. If you have a sequence where the terms are all positive, then that sequence goes to infinity if and only if the limit of the reciprocals is 0. Okay, so maybe this is, I think this is a good one for you to try. Right? This is pretty straightforward. So take 1 or 2 minutes. Take 2 minutes and see if you can get, say, the forward direction. Okay. So try to show that if the limit is infinity, that ensures that 1 over. So this should be pretty straightforward. So just write it down. Why? Somebody's trying to jazz up the last day before vacation.
I'm a fan.
This is, what's the name of this piece? It's by Mahler? Is that right?
Is this like the Star Wars thing?
No, this is
Star Wars. Is it like
this is not Star Wars. This is from 2001. Space Odyssey.
Space Odyssey.
But it's actually a real classical piece, right? I think by Mahler. I think. And that is the proof. Okay, talk to somebody nearby about what you wrote or about anything.
I guess I was thinking about that definition, and how it says it is bigger than
I say,
I'm trying to feel like that.
since you know
And then like,
is infinity.
this is very big, and so we have bigger than some. Then I was kind of confused how to like finish it.
Is greater than. You can say that, and then flip it
That
around.
was really good.
Take the error term, set the error term.
What if we just,
And then so you can say the opposite.
what is, like, what do we need to show something incongruous is zero? So we can read it is less than, so this is actually one of the something that's less than.
Yeah, because it's almost like the sum charges, you know.
So if we take the.
If we set that higher, we set this now.
So that's the same as saying,
Shrinking it down closer to zero.
isn't just,
On the error
if we just put epsilon equal rad, and then we're done.
Approaching zero.
Mhm.
We're saying like, this is less
Is that
than.
kind of the way you did it?
Yeah.
Okay.
Okay,
Yes.
so let's look at this, right? So here's what we want to show, right? That the limit of 1 over s sub n is 0 as n goes to infinity, right? So that's our old limit, right? Not the infinity limit, right? So to play that, to solve that, to show that, we need to play the epsilon game, right? So given any epsilon, there exists an n such that if n exceeds n, then the distance between 1 over s of n and 0 is less than epsilon. Now that's the same thing, right? Because these guys are positive, that's the same thing as saying that this is true, right? Right. Okay, but that's the same thing as saying that s of n should exceed 1 over epsilon. Right? Right? Okay, now we're given that s of n goes to infinity. Right? So who can tell me what I should write here?
Given any capital
Just a
N-
second. Sorry. Since s of n goes to infinity, yeah, go ahead.
Since S of n goes to infinity, given any capital M greater than 0, there exists a big N such that if n is greater than big N, S of n is greater than M.
So,
So 1 over S of n is less than 1 over M. Right? And then epsilon equals 1 over n.
okay, yeah, so take your M to be 1 over epsilon. Right. So let M be 1 over epsilon. Right. Since S of n goes to infinity, we know that there exists a time past which S of n exceeds M, which is 1 over epsilon. Right? But that's the same thing as saying that epsilon is bigger than, well, that's the same thing as what we, that's it. Right? Which is, so this is what, which is what we needed. We needed to find an n such that if we're past it, then S of n exceeds 1 over epsilon, and this guy goes to infinity, so there is such an n where everybody's bigger than 1 over epsilon. Okay.
But
Yeah.
Are we supposed to find, you say that any M, that's true?
Say it again.
Are we supposed to say that any M, that is true?
You're getting mixed up between, so we want to show that for any epsilon, we can make these guys bigger than 1 over epsilon.
Oh, and we're just using the fact that any M on the right side to find just one M.
Right.
That's
We
true.
know that for any M, we can play this game.
Got it.
So take our M to be 1 over epsilon. Well, then we know that there's a time past which we're greater than that, and that's what we want. Okay, that's it for today. Have a nice break, everyone.